everyone who's not here.
Yeah.
Today we have Chentai to have his PhD dissertation defense. And Chentai get a bachelor degree from Purdue University. He is originally from Malaysia. And then he entered the PhD program here in 2015. It's a long time. Chentai, now is the time for you to defend.
Yeah.
I'll give it to you.
Okay, thank you. Good afternoon, everybody. My name is Chin Chai, and thank you very much for coming to my defense today. Just to let you know, the format will be in person and also through Google Meet for my friends and family, and for those who cannot make it today. Again, my name is Chin Chai. For the past few years, I've been working with Dr. Jiang, and with the help of my committee, and today, really gracefully, I'm able to present my topic to you: the redox change across the late Cambrian, septonium positive carbon isotope excursion in the Southern Great Basin. So just before I move into my presentation, I just want you to know like the outline of the presentation. So I have 4 chapters. The first chapter would be the overall introduction. In this chapter, we'll be talking about like what happened in the late Cambrian period, what is the late Cambrian period and what happened there, and what was the problem, and what my research trying to solve. And then for chapter 2 and chapter 3, we'll be discussing the redox proxy I'll be using. Here we'll be talking about rare earth element, and for chapter 3, we'll be using uranium concentration to as a redox proxy. And chapter 4, we're going to shift the attention a little bit to go to the Death Valley and do some sedimentological study. The late Cambrian period, which is around 500 million years ago, recorded one of the largest carbon cycle perturbation known as the septonium positive carbon isotope excursion, or SPICE. Some general characteristics of SPICE are it lasted for 2 to 4 million years. The magnitude is around 4 per mil to 5 per mil. It is not a local signature, but it was documented from the world succession. Many studies have attributed that the cause for the SPICE event was because of enhanced organic carbon barrier. So this is the time scale. We are here today. So this is where the SPICE event was documented. This is just a generalized curve of SPICE event documented by Sussman 2012. So this diagram will show you the SPICE event is not a local signature, but it was coming from, you have the data coming from Siberia, South China, Kazakhstan, the USA, the UK, and then Australia, and some other places. Because long-term organic carbon barrier would leak oxygen into the atmosphere, and from the mass balance carbon and sulfur isotope prediction that there's a lot of oxygen being associated with the SPICE event. And because the SPICE event happened at the boundary between the Cambrian and Ordovician, and at the beginning of Ordovician, there was a great Ordovician biodiversification event. So it is believed that the oxygen that being released from the SPICE event may have triggered the great Ordovician event. So I compiled some data, the redox data, to see what happened, what people have done, and what are the outcomes. So here we have data coming from mercury concentration, and then uranium isotope, sulfur isotope, ion speciation, molybdenum isotope, and other redox sensitive data. All these redox proxies consistently show that during the late Cambrian period, there's no oxygenation event, but they point towards an anoxia widespread condition during the SPICE event. So here comes my research. My research attempt to use different carbonate-based redox proxy to test the oxygenation during the SPICE event. Here comes my chapter 2. My chapter 2 will be using the rare earth element and yttrium. Here I'm going to refer them as REY, particularly the serum anomaly as the redox proxy. And chapter 3, we're going to look at uranium concentration as the redox proxy and see what do we have. So let's talk about the study location. So my study location is in the Great Basin. Why? Because the Great Basin during the late Cambrian time, it was believed to be connected to the open ocean. That's why it should record the global seawater signature. And the fact that it is well exposed and continuous, you can easily document it in Nevada and Utah. And also the section is dominated by carbonate lithology, allow us to perform the geochemical analysis. So this is the generalized carbonate platform in the Great Basin during the late Cambrian period. I have 3 sections. Number 1 will be the house spring section right here, and then single pass right here, and also Table Canyon right here. So if you look at Nevada and Utah during the late Cambrian time, so house spring section is right here, single pass, Table Canyon. The Nevada side, like the California side, is more like a deeper environment, where the Utah side will be like close to the land. So let's explore, let's understand, let's go to my second chapter, which will be using the REY as a redox proxy. So before we learn about this REY as a redox proxy, let's learn the background information of the REY. So the red element is the 14th element that can be found here in the periodic table, And how is the red element being transported to the ocean? It can be through riverine input, hydrothermal input, aeolian input, and the major input to the ocean will be riverine input. So many studies have done look at the overall distribution pattern of the REE, and then this is a summary. So at different deposition environment, you will see different distribution pattern. So for example, you look at the red color one. If you look at the deposition environment where there's hydrothermal input, you should see like a positive European anomaly. But here we're going to focus on the light blue region, which is this one. This is the modern seawater signature. It has some characteristic. So the modern seawater signature REY distribution pattern, you should have a slight lanthanum anomaly, and then you will have a negative serum anomaly. I'll talk about what negative serum anomaly means in a minute. And then you should have a light RE relatively depleted. So light RE means like the RE like here, like light RE, because the light RE is preferential to be removed in the seawater. That's why you have a depletion signature here. And you also have a high yttrium over holmium ratio, more than 36, that would indicate a seawater signature. So yttrium is not a REE, but it's often used to compare with the holmium because they have a similar chemical property. And because in the seawater, holmium is easy to be removed. That's why you have a high yttrium over holmium ratio. So let's learn about the serum redox behavior in the ocean. So serum have two oxidation states, serum 3 and serum 4. In an anoxic condition, serum 3 will be removed to become serum will be reduced to serum 3, and serum 3 is soluble. That's why it's present in the dissolved form in the water. You have relatively enriched in the seawater concentration. And then you have a positive anomaly. So for example, in the Archean time when there's no oxygen, all serum will stay in the reduced form, and then you have a high serum anomaly. As compared to serum 4, we have serum 3, we have serum 4. So serum form in the oxide condition is being oxidized to become serum 4, and it is relatively insoluble. So when it's insoluble, it's easy to be attached to the iron and manganese oxide or particulate and sink down to the sediment. And in order to remove from the seawater column, that's why you have the depleted concentration in the seawater, and then you have a negative anomaly. So for example, in the modern ocean is considered oxygenation, so you have a low serum anomaly. So how do we measure the trace element, red element, and major element of all the sample? We've done all this thing at the Nevada Plasma Facility Lab. We use ICP-MS to do it. The very generalized method to prepare the sample will be, we have a rocks. We're going to drill the rocks, and then you take the powder, 10 milligrams of the powder, you dissolve it with the 5% base-like acetic acid, and then you're going to transfer the supernatant into Teflon beaker, and then dry at 100 degree, and then you're going to dissolve the residue with the double distilled nitric acid, and then the last step will be you dilute the water sample, and the sample solution are ready for chemical analysis. And then we run each sequence twice because we want to make sure the reproducible data. So this is the lab. So before moving into the geochemical data, let's look at the overall stratigraphic framework in the Great Basin during the late Cambrian period. So here I'm able to correlate this 3 deposition environment with the sequence stratigraphy, chemostratigraphy, and also biostratigraphy. So the correlation here, 5 interval is being identified. So this 5 interval cover 4 biozones, which are the Crepicephalus, Aphilophis, Dundenbergia, and Albinia biozone. And so the biostratigraphy you can see here. So for the chemostratigraphy, it can be divided into 5 sections, which is before the excursion, which is right here, and then the rising limb of the excursion, and the peak of the excursion, the decreasing limb. This is not very good for decreasing, so here's like the dropping limb of the excursion, and then after the excursion, which is right here. For all the 3 deposition environments, we see the spice event nicely documented on all these sections. So the gray data point would be the data from Saltzman 1998, and then the blue data point would be from this study. So now let's look at each stratigraphic section in detail. So let's look at the Haltran section first. So here we need to focus, we have 5 formation here. So we have low energy environment. The low energy environment will be like a shell limestone here. So shell and limestone, waxstone is like kind of in the low energy deposition. But we also see some high energy deposition. For example, like a wavy, microbial like a grainstone, and oolites. You see some oolites here. Oolite usually lives in a high energy environment. And then you also have like a different fossils here can be documented. So for the Huan section, it is the deposition environment for this section would be the shelf environment, which is the high energy, but you also have some kind of protected inner shelf environment, like kind of fluctuation between shelf and inner shelf. For a single pass section, this is pretty straightforward. You see there's a lot of like a big high energy deposition, like the grainstone, and a cross bedding, wavy, microbial laminate. There's a lot of grainstone, and then there's some crack you can see right here, and then oolites as well. So all this indicate like high energy environment. So the single pass section was deposited in the shelf marine and margin environment, and above the fair weather wave bank. This is really high energy, like close to the surface of the water. So now we have the Taibo Canyon section. So the Taibo Canyon section you can see here is like pretty shale and low energy wax limestone. This is all like very low energy environment. So basically this is what happened, like you have a slope, and then the turbidite, the debris flow on the top, and then like the bottom you have like a low energy environment. So the whole Taibo Canyon section was deposited in the slope environment. So again, back to this diagram. Back to this diagram, we have the Huan section, it's right here. Shelf, inner shelf, kind of fluctuation a little bit. Single pass, the shelf margin, and then the Taibo Canyon. So this is like a debris flow. This is the Taibo Canyon section. Okay, so this is the geochemical data we have from all this section. There's a lot of things here. So I'll just summarize the important thing we're going to talk about. So overall, the three sections across different deposition environment, we see high serum anomaly. The range is between 0.8 and 1.2 across the whole all the section. And then we also see high yttrium or chromium ratio, like more than 36. If you remember, more than 36 is the indication of seawater signature. And then we also see the carbonate percentage. For all of the averages, like majority of them more than 80%. Some can go to up to 90%. For Taibo Canyon, the average of the carbonate is a bit lower. We also see low thorium concentration. Low thorium is used to determine the silicic classic influence. So the low thorium concentration tells you that the section that we have is not being controlled, influenced by the silicic classic influence. Let's look at the overall REY distribution pattern. So here we see the slight LA anomaly, and then remember slight LA anomaly and the high yttrium over chromium ratio, the seawater signature. And here we see positive, there's no serum anomaly at all. If you treat all this, there's no serum anomaly. And then you also see light REE relatively enriched. It's like kind of flat. There's no like heavy RE enriched here. So these two characteristics shows anoxic condition. So because with carbonate can be subjected to different kind of contamination. So here we're gonna look at the evaluate the silicic classic contamination. We plot the serum anomaly against aluminum because aluminum is a silicic classic dominant element. There's no correlation at all. We also plot serum anomaly against the yttrium or chromium. There's also no correlation. It tells you the silicic classic contamination is minimal. So what happens is our data shows that positive serum anomaly is being documented across the whole basin, right? Across the whole basin, even at the really low energy, high energy environment, the single pass section. So it tells you that anoxic condition is not only happened at the bottom water, but it was all expanded all the way to the shallow water environment. So this is the ocean condition. So what about the Lake Cambrian atmospheric condition? So let's do some comparison here. So the Paleoproterozoic period, which is around 2,500 years to 1,600 million years ago, they also have the same phenomenon. The high energy environment actually also documents show the positive serum anomaly. Because the atmosphere and the ocean often achieve equilibrium, so when you have an anoxic condition in a high energy environment, it will be reflected to the anoxic condition in the atmosphere. But in the Lake Cambrian period, it's a little bit different. Because the Lake Cambrian period, so in the Lake Cambrian period, we also see the single pass section, which is high energy environment, also show anoxic condition. But we cannot use this anoxic condition to reflect to the Lake Cambrian atmosphere. The reason is because the Lake Cambrian period has been through the Neoproterozoic oxidation event and some other oxidation event, so the atmosphere must have some kind of oxygenation there. So why is the atmosphere have oxygen level, some kind of oxygenation, but the high energy environment still show anoxic condition? The possible reason could be during the Lake Cambrian period, the ocean and atmosphere, they are not in the equilibrium form, they're decoupled. or it could be still a very thin layer of oxygen, thin oxygen layer in the Lake Cambrian Ocean. But this layer is so thin that it's even above the single pass section that is not shown in our section. So I also compiled data from like 3.5 billion years today to look at the circular serum anomaly change through time, and together with the data from Liu et al. 2021. So here you can see negative serum anomaly usually documented around the oxidation event. So the great oxidation event, you see like a spike here, and then you see neoprotein oxidation event, you see this like really negative serum anomaly. But for the positive serum anomaly, it usually documented at the very anoxic condition, what Archean, and also between these two periods. So it's like anoxic condition, you have high positive serum anomaly. So the conclusion for chapter 2 is we look at the Bayesian correlation based on the stratigraphy, sequence stratigraphy, chemostratigraphy, and biostratigraphy, and we interpret that house range section was in the shelf environment, single pass was in the shelf margin, high energy environment, and table was in the slope environment. Look at we evaluate the diagenesis, cross-plot diagram show that there's no Silis class influence in our sample, and the Yichim over Homing ratio showed more than 36, majority of them, and that's the seawater signature. And positive serum anomaly was documented throughout the whole section, the whole basin across different sections. It tells you that the anoxic condition not only in the bottom water, but expanded all the way to shallow water. So the conclusion here is, using the serum anomaly, the Great Basin during the Lake Cambrian period, there's no oxygenation being documented during the spice interval. So now let's move to my chapter 3. My chapter 3 have two parts. The first part will be evaluating the potential of using uranium concentration in carbonate as the redox proxy. And the second part will be looking at the uranium concentration change across the spice event. But however, using uranium concentration in carbonate as the redox proxy has some uncertainty. Let's see what are the uncertainty and see if we can solve them. So uranium have two different oxidation states. We have uranium-4 and uranium-6. So in the oxide condition, uranium-4 will be oxidized to become uranium-6. Uranium-6 is soluble, and so when you have soluble, it's present as a dissolved form in the water column. That's why you have more higher concentration enriched in the seawater. In the anoxic condition, uranium-6 will reduce to become uranium-4, and it's less soluble, and it will be attached to the iron or manganese particulate and sink down to the ocean sediment. In another word, it removed from the water column. That's why you have the depletion in the seawater column during the anoxic time. This diagram will show you how uranium is being transported to the ocean. So uranium being transported to the ocean through three different sources. The major source will be the continental weathering. So after uranium being transported to the ocean, to the seawater, they will experience some kind of sink. So uranium can be precipitated out into carbonate, or it can be removed by the sediment, anoxic sedimentation, or being absorbed to iron and manganese particulate and removed from the seawater column, or it can be removed by the altered basalt. There are some potential diagenesis that will release uranium back to the seawater. For example, reoxidation of the organic matter might release uranium back to the seawater. So now let's look at the modern ocean, modern environment, the largest carbonate platform, which is the Bahamas. I'll compile some data to look at how is the uranium content in the Bahamas. So here we're going to focus on uranium concentration here and uranium isotopes. So uranium isotope here in the modern ocean show a pretty narrow range. It ranges from negative 0.525 per mil to 0.48 per mil. It's pretty narrow. And uranium isotope is well developed as a redox proxy. Many studies have used it to reconstruct the redox condition. But here, for uranium concentration, you see the range is 0.0231 ppm to 4.33 ppm. It's a big range. And it's a big range. So many laboratory experience have shown that the partition coefficient of uranium into carbonate are different. It's really high into aragonite and it's really low for calcite. As you can see here, the calcite has a low ppm and the aragonite have the high, relatively higher concentration value. So now let's look at some ancient carbonate. So we have the data from PT boundary. So in this example, I'm going to focus on the relationship between uranium concentration and uranium isotope. So you see there's no correlation at all. They're totally not in the same pattern, right? So another example is coming from Ediacaran. So this section, 3 sections, they were deposited in the same time interval, but you see the uranium concentration show like completely different thing. And both of these studies have agreed that the reason why the variation in concentration, uranium concentration happened here is because of the mineralogical effect, which is the different carbonate mineral. So now let's look at in a well-preserved carbonate. So I compiled data from different studies across the major anoxic event and see how the uranium concentration changed in this major anoxic event. So here I want you to focus two things. Number one is to focus on the relationship between the uranium isotopes and also uranium concentration. So you see all of them show like a covariant relationship, all of them. And then the second observation is, for example, for the PD boundary, so the Permian is still oxy here, and the Triassic is anoxic. So you see the uranium concentration show a abrupt decrease across the anoxic period, like for consistently all across all this major anoxic event. So another step forward to evaluate the potential of using uranium concentration as a redox proxy, I compiled data from 3.3 billion years to today and look at the overall circular change of uranium concentration in carbonate and compare it to the black shell. The reason why I'm comparing it to the uranium concentration in black shell is because the uranium concentration in black shell is a widely developed redox proxy. Many studies have used the uranium concentration in black shell to reconstruct the redox condition. So here, you see the consistency between these two comparisons. And also, another step forward to evaluate the potential of using uranium concentration as a redox proxy, I compared the uranium concentration in carbonate with other more developed carbonate-based redox proxy. So in this diagram, you see we have data from uranium isotopes, zinc, sulfur isotope, iodine, and serum anomaly, and all this circular trending show consistency. They show that the increase of concentration during the oxidation event, which is right here, you see like a spice of increase during the oxidation event here, and then the second rise would be the neoproterozoic oxidation event. You see like the rise of concentration like somewhere here, and you also see during the phanerozoic, all the concentration remain high because of the relatively more oxygen available in the system. So the first conclusion of the first part is the data compilation show that in well-preserved carbonate, uranium concentration in carbonate can be used as the redox proxy based on the consistency we just talked about. Let's now move on to my section in the late Cambrian period. So to remind you, I have three sections. We have the house range, the single pass, and the tidal canyon at the different deposition environments. Now we're going to test the oxygenation across the whole basin. So here, I have three sections. We're going to look at the uranium, is the red color here. We see some observation. We see depletion of uranium during the spice event. You see the uranium concentration show like obvious decrease during the spice event, and then you see like a noticeable increase after the spice event across the basin. You see they're all like at a different deposition number, like really low depletion during the spice event and increase across the basin after the spice event. Of course, again, we're going to deal with the silicic classic contamination. So here we evaluate the silicic classic dominant. We look at aluminum and thorium. So aluminum and thorium is really low for all the section, okay? So it tells you the silicic classic dominant, silicic classic influence is not dominant. We also evaluate the cross plot diagram. I'll show you in a little bit. And then we also consider the fact that the signal you see just now is not only happening in one section, it's happened across the basin. And given that we have different lithology, different phases, but the uranium concentration still consistently show the same thing. So we believe that the uranium concentration doesn't affect by the lithology or phase or other factors, but it was the primary sequence signature. So now let's look at cross plot. I plot thorium over aluminum. It shows that they have a positive correlation. It tells you they are both from a silicic classic origin. When I plot uranium against aluminum, there's no correlation. It tells you silicic classic is not dominant. So the conclusion, the second conclusion of chapter 3 will be we see low uranium concentration during the spice event. It is so low, and it's even lower than the upper crust value, like 2.2. It means that uranium during the spice event are all being reduced to uranium-4. Uranium-4 is considered insoluble, and anoxic sedimentation will remove all this uranium-4 to the sediment. That's why it creates a small uranium reservoir in the seawater. That's why you have a low concentration. And also, noticeable increase of uranium after the spice event. It could means that the seawater may be recovering, have the uranium reservoir recovery. But we need more data to confirm that. And our data also show consistency with the Appalachian Basin during the spice event. You see the uranium concentration here is really low during the spice event. So we are also like around like less than 1. It's the same with other basins. So to conclude for chapter 3, we have two conclusions. Number one is uranium concentration in raw preserved carbonate can track the redox change. And the second one will be no oxidation is being detected during the spice event from the uranium concentration in carbonate. So chapter 4. So chapter 4, we're going to shift gear a little bit to the sedimentological fossil study. In this chapter, I will be explore the origin and the origin and deposition environment of the Johnny oolites. So let's see why is this study important. The Ediacaran period recorded the largest negative carbon isotope excursion, which is the shroom excursion. And there's a lot of study debating if the shroom excursion is caused by the primary signature or the secondary signature. In Death Valley, the Johnny oolite bed preserved the onset of the shroom excursion. So by understanding the deposition environment and the origin of the Johnny oolite may help us to understand the origin of the shroom excursion in the Death Valley. But first, what is ooites? So ooites are coated grain sedimentary rocks, and it can be found like pervasively in the geology in old time and also in the modern environment. So it can be from fresh water and salt water. The size is really small; it's like less than 2 millimeter, and the shape is like spherical shape, and usually composed of like a concentric cortex lamination, and then there's a nucleus in the middle. It looks like that. So currently, there are two concepts about the origin of the ooites. So the traditional view that the ooites was formed in an organic condition. So what happened under this theory is you have a really high agitated environment. A nucleus is being introduced to this condition, and then it will start forming like the layers of the ooit around the nucleus and become ooites. The advancement of the nanotechnology and the detection of the microbial evidence have led to a new hypothesis that ooites can be formed through organic through the organic way. So under the organic concept, two things are very important, which is the EPS and also ACC. EPS is the extracellular polymer substances, and ACC is the amorphous calcium carbonate. So these two things are very important when it comes to interpret the under the organic concept, because these two things serve as like a medium or like a stage for the microbes will carry out like activities. Okay, so for geological background, the Death Valley, this is the geologic map of Death Valley during the Ediacaran period. So we have Las Vegas right here. This is I-15, this is Bakers, and then we have 4 sections. Number 1 will be here, the North Mesquite section. Number 2 will be Southern North Range section. Number 3 will be here, which is the Cedar Peak here. And then number 4 is Odette Mountain, which is right here. So let's look at the stratigraphy of the Johnny Formation. So Johnny Formation was overlain by the steering and overlying the Noonday Formation in Death Valley. And then a Johnny Formation composed of mixed siliciclastic and carbonate lithology, which tells you it's like a shallow marine with the fluvial inference. And here, the Johnny Formation can be divided into 7 sections. The top one, the top division, will be the rainstorm member, which is the uppermost section. And then this is the stratigraphy of the rainstorm member. The shroom excursion is documented like here and also here. In this study, we're going to look at the Johnny oolite only, which is the distinctive biomarker in Death Valley. So the method we're using for this chapter would be we're going to go to the field and do some sedimentological observation, including the sizes, geological feature, thickness, and colors, and stuff like that. And then we're going to also look at the petrographic study. We're going to do some thin section and see the overall structure of it. And then we're going to perform the FESEM and try to see the micro features of the ooites, and also, if possible, the microbial evidence. And then we're also going to see some geochemistry of the Johnny oolites. So let's talk about the FESEM, the step I'm using. So I use the tweezers to handpick the ooites grain, and then put it into the ultrasonic device, clean it with the distilled water for 20 minutes, and then coat it with gold, and then put it underneath the FESEM for some EDS and also some micro features observation. So the field photo, you see all this, the color, number one is all orange, you see joining one is orange color. For the North Mesquite section, it's over, you see the top and the bottom is pink shell, it's a pink color shell. And then you close up, you see this is how it looks like. And then for this section also have pink shell here. And then this is me, and this is the South North Parliament section. It's like a biomark you can see. And then for some section, it's pretty deformed. This is Saddle Peak Hill. And then we have the Odat Mountain. You see some interclass in the Odat Mountain section. And Odat Mountain section is a thinner section. So we have different thickness. So the South North Parliament is the tallest, is the thickest. And then we have the thinnest one is the Odat section, Odat Mountain section. We perform high resolution sampling, like around 20 to 20 cm for the carbon isotopes. And then yes, we do document the onset signature of the stream excursion in all the section. So now let's look at the petrographic study. So something you're gonna pay attention. We have some recrystallized. You see some broken one, so like some broken oolites here, and then some recrystallization being detected right here. And then this is a pretty well preserved ooid. You have a nucleus here, right? The size is about 2 mm. And then polysorted, you see polysorted. So this is like big, this is very big, very small. And then you look at the size, this is so big, and this is such a small size, like 1 to 4, maybe more. And yeah, it's the same thing, very poor sorting, around 2 mm, broken. And then this is pretty well preserved. For this one, we have the Saddle Peak. Saddle Peak is also pretty good preserved. We have the aggregate one here. You see like a 3 wood trying to like fuse into one. And then poor sorting, really poor sorting, 1 to 4 ratio. Some organic matter here, you can find. And then this one is pretty nicely, you can see the different layers of the concentric cortex lamina. You see like pointed by the red arrow, different layers. And then, so now let's look at the FESM picture. So before I explain the FESM, I want to let you know this is how I do it. So I see a grain from far and then like slowly from the outside and go to the inside. If I see anything interesting, I'll focus on that particular region and take some picture. So this is the outer surface of the oods under FESM. Okay, so when you move it a little bit more, you see like there's a big grain here. Difference between really big grain and very small grain here. So I focus here, this is C, so C is here. So you see the crystal size is really big. And then when you go to like a D, you see this is where D is. So D is like a really fine grain, and then you can see like a cross section of the needle like pointing towards you like that. And then when you go to E, so I see some kind of like a interesting thing. So this will be here F. So I focus them. This is what I see. I see like a white layer thing. It looks like an EPS thing, kind of white layer thing. You have like a nanoparticle here present in this layer. And I also see some bacteria, like a cyanobacteria here. And then this is like, you see the wall, it's like a gap, and then you see kind of particle between them. So although we see some kind of microbial evidence, but the microbial evidence is extremely rare and it's extremely limited throughout the ooid grain. So now let's look at the EDS. So we do some scanning. This is the ooid grain, right? So we have a lot of calcium, a lot of magnesium, really high calcium and really high magnesium. Makes sense because this is dolomite. And then you see the middle one is really high in silica. It's a silicic classic dominant, like a silicic classic detritus in the nucleus. So before we talk about the Mg or calcium ratio, so this is the background. So microbial activity will preferentially use calcium. That's why if microbial activity present, you will have a lot of calcium being used, so you will have a high magnesium or calcium ratio. So you can see here, the magnesium or calcium ratio is consistent throughout the whole ooid grain, like there's no change, pretty consistent and pretty low. So when it comes to the origin of the joining ooids, if microbial activities control the origin of the ooid, the joining oolites, control the origin of the joining oolite, you should see pervasive and easy. You should see a lot of microbial evidence throughout the whole shell, like a lot of them and widespread. But in this case, it's not like that. So we see very inconsistent and very limited microbial evidence. The presence is very insignificant. Together with the observation of the constant magnesium and calcium ratio throughout the whole thing, we came to the conclusion that all these things suggest that the joining oolite was abiogenetic, was deposited in organic condition. So now let's look at the deposition environment. A lot of studies have shown that the radial orientation microfractal needle was formed in a low energy environment. But we see different sizes. We see the big one and we see the small size. And the overall sorting is really bad. So all this information suggests that the ooze was formed at a two different deposition environment. The big one can be formed in the high energy subaqueous sand dune, and the small one can be formed in the low energy interdune environments. And then the migration happened and migrate all these two grain sizes into one place where the Johnny oolite is. Overall conclusion, the title, I have a title for each of them, and the title is kind of tell you the overall conclusion of each chapter. Chapter 2, we have widespread late Cambrian ocean anoxia implied by the constant serum anomaly across the septonium positive carbon isotopic excursion spikes in the Southern Great Basin. And for chapter 3, two parts. The first part will be the potential of using uranium concentration in carbon acid redox proxy. Second part will be uranium concentration change across the septonium positive carbon isotopic excursion in the Southern Great Basin. Chapter 4 would be a biogenic origin of the Precambrian Johnny oolites in the Nile Valley, deposited in the relatively low energy environment. Okay. Okay, so this dissertation was done during the COVID time. So it made me extra grateful because there's a lot of things that we're not sure. So with that, I want to thank you for the UNLV for the really thoughtful and safety plan for all the students, and also the really quick response from the geoscience department, because when we have a question or we have something we're not sure, the department acts so fast, so quickly to answer all my questions. So with that, thank you for the geoscience department. And this decision cannot be possible without my advisor, Dr. Jiang. So he's a really smart scientist and really critical. It provide me all the connection and provide me all my everything possible for me to finish my dissertation, the correction and everything. And thank you, Dr. Lockney, for willing to take a month, the whole semester, last semester, with me to correct and improve my dissertation. Thank you for that. And another thing I want to talk about, Dr. Lockney, is first semester when I was robbed, you sat me down, you talked to me. One time you sat me down and talked to me, like asked how was I doing, and then you give me a lot of suggestion about where to live and whatnot and stuff like that. It was really nice. Thank you for doing that. I really appreciate it. And for Huan, so when I look at my dissertation, I feel like if I don't have the data from your lab, pretty much I don't have a dissertation at all. So with that, thank you so much for generosity for allowing me to use your lab and also teach me through the whole thing. And for Libby Hoff, Dr. Libby, thank you. I know you're very, very busy, but every time I talk to you, you're so encouraging. And then you give me a lot of comment for my decision to improve. And one small thing you did that I really, really appreciate is whenever I talk to you, or maybe when you sit in the desk in the room, you always do your nodding head, right? So when I'm not really confident, well, I'll look at you, and then you just make me feel a little bit confident. So thank you for doing that. And for Dr. Stephen, thank you. Thank you for your time. I know you're from an engineer perspective. So I remember my first comic exam, you asked me a question. I wasn't expect any question from you, but when you asked me the question, I didn't even know how to answer your question. So every time when I have a meeting with you, I have to like think other than the geoscience, maybe from another perspective. So thank you. Thank you for your time. So thank you. I really appreciate it. And UNLV is a really good university, especially the Department of Geoscience. So all the data you see up there was all done at UNLV. So with that, I want to thank you, the Las Vegas Isotope Labs, and also the Nevada Plasma Facility Lab, and also the Electron Microanalysis and Imaging Lab. Thank you, Dr. Ren, for the whole FESEM guidance and all the discussion we have. Thank you very much. And also I want to thank you for my friends and family, both in Malaysia and here. Thank you for the support. Thank you for everything. So I never thought of having a chance to study in the USA. With that, I want to especially thank you, the two big financial support I have. Thank you to the Malaysian Public Service Department supporting my bachelor. And also thank you for the Nevada System of Higher Education for giving me the chance for my PhD. So that's me for my kindergarten and then high school and bachelor. And with that, I have met a lot of good teachers along the way, the whole journey from my kindergarten all the way to today. I've been able to talk to you today because I applied knowledge all the way from this whole process. And thank you for all the teachers I met and friends and to be able to finish this. And dedication, so my father passed away in the middle of my dissertation. I feel really, I didn't spend the time with him. So thank you. So this is the picture I have both here and also in Malaysia. Really, really thankful. Thank you. Okay, I have something to say for this. Wait. summary. This is a summary for the 7 years of geology at UNLV. This 7 years, we've been through like really hot, low time and high time. We have been through a very cold time, like Utah cold time, really hot time, like a hot valley, that valley hot time. And sometimes it's not easy, but you know what? All of them, we get through all of this, we get through them. And sometimes we get really dirty, and then we clean up, and we suit up, and we're able to present what we have to the community. I think these are very beautiful pictures. Thank you. And that's your calendar picture. I think this is a very nice picture captured by Debbie. It shows different posting I have in the Death Valley. It's very nice. But there is a meaning for this picture. The meaning is I've learned a lot since I picked up the hammer from the lab management, the field works, and data interpretation and everything. And for the whole process, throughout the whole process, GQ was always here for me, with me, and to help me. With that, thank you. Thank you for coming for a presentation.
Okay. Now, the non-commit members, if you have questions to ask Chen-Chai, please go ahead now.
Yes.
Simple question, or maybe you mentioned it, but so today you can get new lights forming in a couple areas of the world, like Bahamas. Is there any evidence of any microbial activity from modern blue lights, or is that just something we're testing for the game?
Yeah, I think there's some in the Bahamas. Yes, I think they have some microbial synthesized one. Yeah, especially the new research. Like when you look at the very old research, it's all like inorganic one. But the FVS and everything, especially, yeah, I see a lot of them. Yeah, especially from the DIAS DICE et al. Florida State. They have a lot of modern microbial control. Yes.
Okay.
Yes.
I will ask a non-scientific question. Can you go back to 2 slides? Okay, on the no, back. Yes.
This one? Oh.
Yeah, that one. So, who is you on the in the band?
Oh, this one.
Yeah. So,
That's.
okay.
Yeah.
So you don't play any.
I do play everything, but I become drum major later on. But I played something before. This is also me here.
Because I don't remember I see playing anything.
Oh, I played something before.
Okay.
When I was at Purdue, I played euphonium in the band. So.
Okay. Okay. Nice.
Yes. Yes.
So uranium going into calcite is
Lower.
lower.
Lower
Yeah.
partition coefficient.
Is uranium like, I don't know, strontium in that it can also be dependent on like sedimentation rate for to get the opportunity, like to get deformation in the calcite lattice to get incorporated, or is it the sedimentation rate not affect uranium concentrations?
Sedimentation rate.
Does the sedimentation rate?
Well, I mean, if you have a really high sedimentation rate, which means you have like for example, like anoxic condition, right? So anoxic condition will definitely have a really high sedimentation, right? That's why you have the black shell and everything form in the really anoxic condition. So I guess yes, because sedimentation rate also can be controlled by the redox condition, and then the redox condition also, when you remove a lot of uranium out. Oh wait, you were talking about like a particular carbonate mineral, or
No.
just in general.
Just in general.
So I think sedimentation will affect the remove of the uranium. Yes. Because you have a lot of black shell being deposited during the anoxic time, and that will take out a lot of uranium. Yes. Thank you.
Other questions for Chen-Chai from the audience?
Yeah, I'll have a lot of things to say to this night. Yes.
With some of the spikes we see, is there any possibility that like meteorite or asteroid crashes into Earth could have affected some of those elements?
The spice, you mean the spice?
Right.
You see the crashing of the meteorite will affecting the spice event. like
Right.
maybe like destroying or maybe cause it or maybe destroy it. Okay, well, I don't think the meteorite effect will be that massive to change it all around, you know, all around the world. And I think if it is caused by the meteorite, the signature is not going to be the spice, because the spice is in the marine condition. So I'm sure for the meteorite, it's definitely not the same you know, concentration we're talking about, same signature at all. Yeah.
Okay.
I don't think it will change it. Yeah.
Those were excellent photos I took.
That's a very excellent. So this is all talked by Debbie. It's a calendar, your next year calendar background.
Any other questions from the audience? Any joke questions?
On the oxidation side, sometimes when there's low oxygen, sometimes when there's high oxygen, is that related in part to plant life evolving or
Yes.
coming into the Cambrian period?
So I guess in the Cambrian there's no land plant yet. So I guess I'll rephrase the question you're talking about. If the land plant gonna change the oxygen, but I think it's the oxygens, the evaluation of oxygen will change the evolution of plant. So the plant, the existing of plant is because of there's enough oxygens present, and then it only comes the plant. Yeah. Of course, the plant come later on, it will produce oxygens. Yes.
Right.
Yes. So I think the plant maybe start in like a Devonian, yeah. But this is Cambrian, it's like way before where there's plant.
I'm gonna try to see if there's any questions from
Oh,
your audience
okay.
without like putting my face in there.
I think there's some word or something. I don't know if that's a question.
Nope, you're good.
Okay. Any question?
Any more questions? If no, okay, the committee is going to toss him for a little bit. So you guys leave, please.
Thank you.